Welcome to Web Handling. My name is Dave Roysum. I am super excited to continue our Materials Matters mini-series with a discussion of width. Why, you say? Well, because width is widely specified, yet very poorly understood, as you will soon see. I know your time is precious, so let's get started. The number one thing to know is that there is no such thing as width, except as defined by some specific testing protocol. While this might seem unusual, it is actually in fact quite common for commercial attributes to be defined by a test rather than some external and universal reality. So while everyone who carefully measures the speed of light or the mass of an electron, even those using different instruments and different techniques, will tend to get quite similar answers, that is not always true for many web properties. There are many ways to measure web width, including calipers, rulers, dual-edge sensors, optical benches, and so on. More importantly, there are many places to measure width, such as on the web or the top of a wound roll. For some materials, that creep when you measure will also matter. Also, any changes in time, temperature, and tension at the point of measurement will affect the value of width that is read. Finally, as with any property in measurement, there will be variability that goes beyond slitting roughness or wound roll edge roughness. So whether you're reporting average, peak-to-peak, RMS, or some other state, you will get different answers. In short, how and when and where you measure width all affect the numbers you report. A fundamental concept is that wound roll width is guaranteed by the inviolate laws of physics to be non-uniform, even if the web width upstream at the cutting blade is perfectly uniform. The roll is wider at the core, medium in the middle, and narrowest at the top. The only exception I know of is netting, because it is not a relatively homogeneous solid, but rather is a structure. With wide pitch netting, the roll width is narrower at the core. The reason for this roll width variation has to do with the physics of pressures inside the wound roll coupled with Poisson expansion. The delta of roll width varies enormously with the size of the roll and the material and the winding conditions. However, something very roughly on the order of 1 millimeter larger near the core would be typical for large rolls of paper and film. However, that value could be much larger on nonwovens, textiles, and tissue. For metals, obviously, the delta of roll width will be immeasurably small, even though it also must respond to the inviolate laws of physics. There are many reasons to be concerned about this, aside from the fact that width is uneven and depends on where you measure it. First, the width increase may be permanent due to creep. Very, very approximately, it would not be unusual for paper and film to widen permanently during storage about half of what the roll width was, or very, very roughly on the order of 1 millimeter for many typical daughter shipping rolls cut from a larger master. This uneven roll end can cause stacking problems if the roll is stacked on the end. This can even cause safety problems in the warehouse and has caused fatalities as stacks tipped over. This uneven roll width also causes a common type of dishing on wide 2-drum winders. So why all this roll width misbehavior? Well, it has to do with the pressure between the layers inside the roll. The pressure is high at the core, medium in the middle, and lowest, or in fact zero, at the outside. This pattern is true for all rolls ever wound of any material ever made on any winder ever made and on any winder settings or combinations of settings you could choose. In short, it is what it is, and you cannot change it. This physics has been known analytically, experimentally, and observationally for more than half a century. It is a bit involved to cover that here, but we do so in quite a bit of detail in my winding book and my Web 101 winding short course. So, if the wound roll pressure is highest at the core, medium in the middle, and lowest at the top, the width will be widest at the core, medium in the middle, and lowest at the top. So, if you know and understand the physics, you will know that physics only allows three solutions to perfectly flat roll ends. Wind under zero tension, variable width cutting, sawing the roll after winding. If you don't know and understand the physics, I will offer you some references shortly. This slide may be a tiny diversion from the topic, but dishing is a common problem on wide two-drum winders, and it interacts with web width changes to make the ends of the roll not flat. While dishing may look like telescoping, it is actually an entirely different set of defects. Thus, there are more than a half dozen totally different types of telescopes and about a half dozen totally different causes of dishing, two of which are shown here. These are covered in detail in my Web 101 training. Both the wound roll edges as well as the incoming web itself has variability. Thus, depending on how you measure and process the data, you will get different values for the width of the web or the roll. Peak to peak, average, and RMS are common metrics. You can find out more about diagnosing rough roll edges in my Web 201.68m clip, so we don't need to do any of that here. No discussion of width would be complete without mentioning a cheap and easy way to automatically measure width continuously and with high precision. That is to use two edge sensors. Not only can the dual edge sensor detect incoming raw material width changes, it also can see the response of the web to moisture, temperature, and tension changes. It can also infer the quality of the splice and also aid in slippage detection. If that were not enough, dual edge sensors can also infer wrinkling, as even the smallest wrinkle will pull the edges in quite noticeably. There are three starting points to learn more about web width and wound roll edge quality. The first is the must-have Ultimate Roll and Web Defect Troubleshooting Guide by Tappy Press. This is an encyclopedia of 500 defects and much, much more. The second is my must-have 750-page web handling handbook. We have an entire chapter on material properties and many pages of test standards in Appendix T that would be helpful for quality control, troubleshooting, and web handling work. Finally, is my award-winning and trademarked Web 101 class that has been taken by 5,000 people just like you. There you will learn about webs, web handling, winding, and some converting operations. It is available as video on demand anywhere in the world by 3 course hosts. Thank you so very much for joining me in this Material Matter series. Stay tuned for the next clip where we will talk about another most important web property, row length. If you have a topic you would like to hear about, let me know in the comment section below. If you found anything interesting or useful here, please like and share and subscribe. Also, please consider supporting the work of this channel using the Patreon link below. See you next time.